In this lesson, we're going to take a look at electric field. Now, this is interesting because we tend to think of forces as contact forces, which means you have to have two objects touching in order for them to exert forces on each other. But the electric force, much like gravity, is not a contact force. It can act over a distance, and those are forces we call field forces. Now, the idea of field was sort of developed by Michael Faraday to describe what happens when charged objects are brought near each other. What he said is if you take a charged object, then it energizes the region of space around it such that any other charge that comes into that region will feel the force. So we draw these field lines as arrows that point in the direction a positive charge would move if it was brought in the vicinity of this charge. So we draw these in terms of a test charge. So if we bring another little charge here, it's going to feel a force on it away from that positive charge. And that force is actually dependent on a couple different things. It's dependent on the charge of this thing, it's dependent on its own charge, and it's dependent on the distance between these two charges. Now, we don't want electric field to depend on this test charge, the one we bring near it. So instead of just telling us the force that a charge feels, so the force on this little test charge is given by, let's say Q is the big charge in the center, little q is the charge that we're bringing near it, r is the distance between them, and then k, right? That's Coulomb's law. That tells us the force on this test charge. But we don't want to know the force on the test charge. We want to know the effect of this charge on any charge that comes within its proximity. And so what we're going to do is we're going to divide this by the test charge. Okay? So that gets us force per charge on this field, or on this thing. And so that leaves us with the electric field vector, E, is given by the charge creating the field divided by the distance to the next thing squared times k, because this q cancels that q. So this is the electric field vector. It tells us the strength of the electric field at any point from a charged object. Now, you have to be careful with this. This is newtons per coulomb. It tells us the amount of force that each coulomb of charge will feel when it's brought into this field at a certain spot. Okay? Now, we use electric field lines, that's what these black arrows represent, to describe the strength of a field. So, let's go ahead and take a look at that. Okay? So these are all charged objects, A, B, and C, and these are all positively charged objects, and we can tell they're positively charged because the arrows point away from the object. We can also tell that object A has the least amount of charge because it has the least amount of field lines going around it. Object B has more charge. Object C has the most charge of these three things. So the closer the field lines are together, the stronger the electric field is at that point, which leads us to this next relationship. Okay? If we have this charged object here, the electric field in close is stronger than the electric field further away. Okay? And the reason for that, well, there's not any more field lines out here, but it does have to cover a greater area, which means these field lines are more spread out than they are when they're close, which follows the equation E equals Q over R squared K. Since we're further away, the electric field is smaller. Now, what happens if we have charges that are interacting with each other? So more than just a point charge. What if we have a distribution of charges? Well, if we had 2-point charges, okay, so this is two negative charges. On a negative charge, you can see the electric field points in towards the charge, and so right here, I get no field. Those two force vectors are going to completely cancel each other out, and a test charge placed here would have a net force of 0 on it. A test charge up here is going to be pulled in, test charge over here is going to be pulled in. Okay, so we get this arrangement. Now, when you have opposite charges, you get a similar thing, except these lines go from a positive to a negative. So if I put a test charge right here, I'm going to have a net force on it towards the negative charge. And so you can see here's like charge things. But these have equal charge, right? They each have the same number of field lines coming around them. If they're unequal charges, then we follow the rule. The one with the greater charge has more field lines. And so if you look at this, this is 2 point charges, same charge. If I put an object here the net force on it is 0. You'll notice that's no longer in between, right in between those. It's closer to the smaller charge because this one's going to have a greater field. It'll exert more force. Okay? And so you can see the field lines for these 2-point charges. Negatives look similar except the field is reversed. Here we have opposite charges, and you can see my positive charge is weaker. It has less field lines, and so this field in like charges, it's symmetric, but in this one it gets pushed closer to the smaller charge, and that same thing happens over here when it's plus minus instead of minus plus. So field lines, they just show us how strong the electric field is, or how much force a charge will feel when it's brought in the proximity of that charged object.